Hi Algebra 2 students, this is Mr. Chen, and we're going to continue our talk on logarithms today. Today we want to be talking about common logarithms and also the change of base formula. Okay, so common logarithms are really the exact same thing as logarithms of other bases. The only difference is that common logs are always in base 10. Okay? So common logs will always have a base of 10, and usually we write common logs without a 10 in there. And you saw this in your investigation. So if you just have log of x like this, that means it's in base 10. Okay? On the TI Inspire, as you saw in your investigation, if you leave the bottom, the base blank, if you leave this part right here, the base blank, then it automatically calculates it in base 10. Okay? And we'll talk more about this later, but this is basically the inverse property of logarithms. And basically, if I have 10 raised to the power of the log base 10 of x, so if the log of x is all inside the exponent of 10, then this simplifies to x. We'll talk a little bit more about this in a more general sense later. Okay, so common logs are just like other logs. They can be rewritten as an exponential. Just notice that here, because even though it's blank, this is base 10, so we can move the 10 up, and it becomes 10 raised to this power equal to 29. So this statement is the same as this statement. It's just one is logarithmic form and one is exponential form. Okay, so I think we can skip this because you've already done this in your investigation, but try this on your calculator. If you put log of 3 into your calculator, you should get 0.4771, and if you put log of 0.2, that is in base 10, you should get minus 0.6990. Okay, so these are the two answers if you do this on your calculator. And you can use your calculator to check. There are several real-life applications of logarithms, and some of these it has uses in chemistry when measuring the pH of a solution, the acidity of a solution, that's the percent hydrogen. You will learn this in chemistry if you haven't already done so, but that's calculated using logs. In the music industry or in any kind of sound measurement device, we'll usually calculate the loudness of a sound in decibels, and that is also done using logs. Also in natural sciences, geologists will use the Richter scale to measure earthquakes, and the Richter scale uses logs to create this continuum to classify the strength of a earthquake. So here, this is a little bit of review here. Remember the one-to-one properties that we talked about in the previous lessons. A to the power of x is a to the power of y. If and only if x equals y, so if the bases are the same, we can drop the exponents down and set them equal to each other. Same thing with logs. The log of x equals the log of y if and only if x equals y. So if we have the log, two logs that are in the same base equal to each other, their arguments will also be equal to each other. And now this, we've talked about this already, but I want to talk a little bit more about these. These are both the inverse properties of logs and exponents. Basically what it's saying is, if I take the exponent of a log and they're in the same base, they will undo each other. They will cancel each other out, and you're left with x. Okay? Same thing, if I take the log of a number that's the same number as the base, and that argument is raised to the x power, then that cancels out and it becomes an x. What I like to do is I like to do a smiley face or a sad face, okay, and I just kind of cancel it out, okay. And so anytime you see log base a of a you can cancel that out. Anytime you see a to the power of log a, you can cancel that out as well. Okay, so this is really important. These are the inverse properties of logs and exponents. Okay, so here's an example of a real-life application of earthquakes. The amount of energy E, okay, so the amount of energy E in ergs, that's the unit, that an earthquake releases is related to its Richter scale magnitude m by the equation log E equals 11.8 plus 1.5 m. The Chilean earthquake of 1960 measured 8.5 on the Richter scale. How much energy was released? Well, this is an example of how logs are used in real life. So let's take a look. Scientists basically developed this formula. They said if I take the log of the amount of energy, that is always equal to 11.8 plus 1.5 m, where m is the magnitude. So m is the magnitude of the earthquake on the Richter scale, and E is the amount of energy in ergs. So we're looking for, the question says, how much energy was released? Well, we're looking for E. So we want to isolate E. So what we'll do is we'll take the log of E equals 11.8. And since we're given M, we're going to substitute M in. We put 8.5 in here. And if we do the calculation, this simplifies to log base E equals 24.55. And you can check that on your calculator. If we now, what we're going to do is we want to isolate this E here. So we want to isolate that E, and the way we're going to do that is by, there's several ways you could do it, but because this is in base 10, okay, if it's a common log, so we're going to raise E, we're going to move that 10 over, and we're going to rewrite it as an exponential. And there you go. This is my energy value in ergs, but that doesn't really tell me much, so let's simplify that. E is approximately 3.55 times 10 to the 24th power ergs, okay? On your calculator, you'll see something like 3.55 ... a whole bunch of numbers, E 24, okay? So anytime you see that, remember that is the same as 10 to the power of 24, okay? So you would write it like this. That's scientific notation, that's calculator notation. You must write it in mathematical scientific notation. Okay, so there's your final answer. Okay, so let's take a look at some actual data close to Korea. This was taken a few days before spring break. So this is the number of earthquakes that occurred around Korea. Okay, so there's quite a few in this region. We're right here. Okay, so let's take a look at another real-world example of this equation that we just talked about. Okay, that equation right there, let's try and use that to find the magnitude, or find the energy released by the earthquake with the strongest magnitudes. Okay, let me just change this to second strongest. So if we find, so why don't you go ahead and pause this video, try to find the amount of energy released by the second strongest earthquake here. Okay, well, if you use this formula, you should have seen that the second strongest is actually this one right here, because it has a 5.1 magnitude on the Richter scale. This was the first one, but we'll use this one. And if you calculate it using this formula right here, you should see that the answer is 2.82 times 10 to the 19 ergs. Okay, so that's the amount of energy released by this earthquake in the Philippines. Now sometimes we'll have exponential equations that don't have the same base. Okay, so it'll be hard to write. It's harder to solve them using the methods that we've been taught. But we can use logs to solve these types of equations. So let's take a look at what these equations are. Okay, it says solve 3 to the power of x equal to 11. So we want to solve for x. I need to find what x is, but right now we have bases, a base 3 and a base 11, okay? And so it's a little more challenging because now we have to use logs. Okay, so what we're going to do is we're going to use the property where we can take the log of both sides, the one-to-one property, where we can take the log of both sides, and I'm just going to go ahead and use a common log, okay? Just because it's easier to use on my calculator. And so I'm going to take the common log of both sides. Well, now this, by the power property, I can bring that x to the front, right? So I'm going to write x log of 3 equals log of 11. And my goal is to solve for x. So right now I'm doing x times log of 3. So I'm going to isolate that x by dividing both sides by log of 3. Okay, so x becomes log of 11 over log of 3. So that would be my answer. That's the exact answer. If I would approximate that using my calculator, and I would get 2.1828. Okay, so that would be my answer if I approximate it into a decimal. Here's another example. We have two bases again on either side of the equation, on either side of the equal sign, that are different. We have one in base 3, one in base 5, so we take the log of both sides, log of 3, all raised to the power of x plus 1, and then we take the log of 5, all raised to the power of 2x minus 1. So, again, we're going to do the same thing. We're going to bring the power, use the power property and bring the powers down to the front. And now we have x plus 1 quantity times log of 3 equal to 2x minus 1 times log of 5. Okay? Now, my goal again is to isolate x, right? I'm going to try and solve for x. So what I'm going to do this time is, because I have factors, okay, I don't like those, so what I'm going to do is I'm going to expand everything, and then I'm going to group my x's together, and then isolate my x, okay? So what happens is I'm going to distribute log of 3 into this x plus 1, so I'm going to get x log 3 plus log 3, and on this side I'm going to have 2x times log of 5, whoops, minus log of 5, okay? And now I have two terms that have x's in them and two terms that don't have x's in them. So I'm going to put those together, get all my x's on the same side, right? So let me bring my x's over to the right side. 2x log of 5 minus x log of 3. And on the left side, we'll have log of 3 plus log of 5. Okay, so log 3 plus log 5 simplifies to log 15, and that's by the power property. We can multiply the 3 and 5. And on this side we get, now we can actually factor out this x here. So we're going to pull this guy out. We get x to the 2 log 5 minus log of 3. Okay, and now what I'm going to do is I want to get x by itself, so I'm going to divide by this whole thing, divide both sides by 2 log 5 minus log 3. So what I end up with is x equals log of 15 all over 2 log 5 minus log 3. And if I punch that into my calculator, I will get, I'll simplify that, and that becomes, and I will get log 1.2772. Okay, so that would be my final answer for x. And you can check that, plug it back in, make sure that it works. Okay, and here's the change of base formula. The change of base formula, really, all it says is I can change, if I have an expression like this, where I have log base a of n, I can change that into an expression, an equivalent expression, where I take the n and it becomes the the argument of the top log, and the a becomes the argument of the bottom log. Okay, and notice that now I've changed the base of my top and bottom logs into something totally different. So here's an example. Log base 5 of 12 can be rewritten as log base 10 of 12, so the 12 goes to the top, and the 5 goes to the bottom, divided by log base 10 of 5. Okay, so this is a really useful formula. It allows us to change complicate logs that are in a messy base into easier bases to work with. Okay. So an example of this, the question says express log base 6 of 8 in terms of common logs, and then it approximate its value to 4 decimal places. Well, log base 6 of 8 can be rewritten as log of 8 over log of 6. Now I could have chosen log base 2 or log base 3, log base 4, but I really don't want to make it more complicated than it already is, so I'm just going to use common logs. And actually this question does ask us to do it in common logs, so this would be correct. Okay, and then you do this, put this into your calculator, and if you do this on your calculator you should get 1.1606 rounded to 4 decimal places. Okay, so that's it for this lesson. Here's your assignment. Go ahead and work these out, and if you have any problems, please feel free to contact me or ask me in class. All right, thank you.